We now take up section 9.3, alternative ways of finding extreme points. And here let's suppose that we have a function f, and the function f has got a maximum at point C. So f has a maximum at point C in an interval I. When I say that x has got a maximum at point C, that means at point C the value of the function is highest. Now that maximum value can be there at the endpoint of the interval. So this maximum value can be there in the endpoint, can be there at the endpoint of the interval. The point to note here is, when I talk about a function f, and we know that there is a point C in the interval I, and at point C in the interval I, the function has got a maximum. This maximum can occur at the end point of the interval. It can occur at a point in the middle of the interval. It can also occur at an end point of the interval. So we can see this figure 9.3, and here we see that there is this maximum which occurs at the end point of the interval, and the end point is this. So here we see that the function f has a maximum, and the point at which the function has got a maximum, that point is an end point of the interval. This is what we can see from this figure. Now let's suppose that this point C is not an end point. So when I write f has a maximum at point C in an interval I can write point C can be the end point of the interval. Now let's suppose that point C is not an end point of the interval. So C is not the end point. C is not the end point of the interval. That's one. And also f is differentiable. So C is not the endpoint of the interval, and also my function f is differentiable. And I also know that the function f has got a maximum at point C. That point C is not the endpoint of the interval, and the function is differentiable. That means it is smooth. And clearly then it's intuitively obvious that the tangent to the graph at point C must be horizontal. It must be parallel to the x-axis. So in this case we can say that tangent to the graph at C must be parallel to the x-axis. Must be parallel to the x-axis. And in other words, we can say that this C is a stationary point because the tangent to the graph at C is parallel to the x-axis, or in other words, f prime C is equal to 0. The derivative, the first derivative of the function evaluated at that point C is equal to 0, because the slope of the tangent to the graph at that point is 0. So if C is not the endpoint of the interval, also f is differentiable. That just means that the tangent to the graph at C must be parallel to the x-axis, and that just implies that C has to be, in this case, C has to be a stationary point. And the same conclusion applies if I start with C being a minimum point. So if I say that the function f has got a minimum at point C in the interval I, this point C is not the endpoint of the interval. F is differentiable. That just means, again, the tangent to the graph at C must be parallel to the x-axis. Again, that means the point C must be a stationary point. What does that mean? That means this condition that C is a stationary point, or f prime C is equal to 0, this is something which is necessary for the interior point C. This condition is necessary for an interior point C at which f prime exists, and this condition is necessary for that point to be an optimal point. What I mean to say here is that once I start with the case that there is a function f that has got a maximum or a minimum at point C in the interval I. C is not the end point of the interval, and f is differentiable. That just means that the tangent to the graph at that point has to be parallel to the x-axis, and that just means that that point, which is C, is going to be the stationary point. So what we see is that this condition that f prime C is equal to 0, this is a necessary condition, in which case this is a necessary condition in a case wherein we have C, we have an interior point C. C is not the end point, please keep that in mind. Interior point C in the interval, and at this point f prime exists. So that means the function is differentiable. At which f prime exists. So this is a necessary condition for this interior point to be an optimal point. When I say optimal, that means either maximum or minimum. So if the point is that this condition f prime C is equal to 0, this is definitely necessary if we are considering an interior point C in an interval and we are considering a function which is differentiable. So at that point f prime definitely exists. In that case, obviously f prime C has to be equal to 0. This is a necessary condition for that point to be an optimal point. It is a necessary condition for that point to be either a maximum or a minimum, as the case may be. Now please keep this in mind that f prime C is equal to 0. This is not sufficient. This condition is not sufficient. That means there can be stationary points, but those are not optimal points. So the point to note is that if you have, so if I say that this is a necessary condition, what I mean to say here is that if you have an optimal point, given the fact that optimal point is in the interior of the interval at which f prime exists, that just means that f prime C has to be equal to 0. But there may be cases when you have stationary point, but it's not an optimal point. So let's take up that diagram. If we see this figure 9.4, here we see that if I talk about x naught, I talk about x naught, x1 and x2. All these three, these are stationary points, but none is an optimal point. Why do I say this? Because if I take up x naught, I know that it is a local maximum point. x1 is a local minimum point. And in fact, if I talk about x2, when I say x0 is a local maximum point, that just means when I say x0 is a local minimum point, that just means that the function f has a local maximum, in the sense that the value of the function at x0 is more than at all neighboring points. Please keep this in mind, that here if I talk about the minimum is at endpoint A. And also I know that the function does not have any maximum, because as x approaches b in figure 9.4, I know that the function approaches infinity. If you think of x0, x1 and x2, I know that all these three, these are stationary points, but none is an optimal point. x0 is a local maximum point, x1 is a local minimum point, x2 is an inflection point. Why do I say x1 is a local minimum point? Because I can see here that the value of the function at point x1 is lower than at all neighboring points, only with respect to the neighboring points. So that is why I say that x0 is a local maximum point, x1 is a local minimum point, and x2 I know there is neither a local maximum nor a local minimum, so x2 is an inflection point. The point to note here is, which is very important, that f prime c is equal to 0. This is a necessary condition for that interior point c to be an optimal point, at which again f prime has to exist. So it is a necessary condition, it is not a sufficient condition. There may be cases when you have a stationary point, but that's not an optimal point. But if you have an optimal point at an interior of the interval wherein the function is differentiable, then that point has to be a stationary point.